Hello, so I'm going to be doing a quick recap on 11.1 of Perms and Combs, or the lesson that was focused on permutations. So a permutation is an ordered arrangement or sequence of all/part of a set. What this is telling you is that you have a certain amount of objects in which the order that you place them matters, okay? So that's what a permutation is. Going to the fundamental counting principle, you know that if you have a task that you need to accomplish and it can be done in an A amount of ways, and then you have a second task that can be done in a B amount of ways, both tasks can be done in A times B ways. And we'll think about that later when we're solving the questions. So a factorial is a way that you can consider the order of permutations. Let's make a random scenario. We have 4 spots on a wall and 4 different books. For each spot, let's just say it doesn't matter where you place the books right now. When you're choosing a book to place in the first spot, you have 4 options to pick one from. Once you pick a book for the first spot, you'll only have 3 options to pick from for the second spot. Then for the third spot, once you pick an option for the second spot, you'll only have 2 options left. Now you've picked a book for each one of these, you'll only have 1 option left for the last spot. Permutations can also involve repeating objects. When it comes to repeating objects, you'll also have a repeating order. As you can see here, different O's are being used for the same word. So technically, these are the same word, but in a different order. Now, with permutations, you want to eliminate the amount of repeating objects, because all you're focusing on is the arrangements. To eliminate this, you first figure out, okay, how many objects do I have that are repeating, and how many objects do I have total? So, in this context, you have 4 letters total. Let's do this over here. You have 4 letters total. As I just showed you, this is how it would go when considering when to place these. However, one of these options are the same. So let's say we're handling pool, or let's just say we're handling this set of letters. You're going to want to divide the total amount of letters to factorial, the factorial symbol, by the amount of letters that repeat. So since O repeats 2 times in these letters, and you have 4 letters total, you would divide 4 factorial by 2 factorial. Let's say there were 3 O's. How you would do that is you would do 4 factorial divided by 3 factorial. So this will be the total amount of numbers that you have, and this will be the total amount for the repeats. If you had a word, let me just make up a random arrangement. You would have to account for both of the objects that repeat. So this has 1, 2, 3, 4, 5, 6 letters. And there is an A that repeats twice and a D that repeats twice. So that's what you divided by to get your total amount of permutations. This is the general formula to be able to solve for repeats. Everything in my notes is the textbook definitions, because that's what he wants us to learn from, but with slightly altered versions to make it more understandable for myself. The general formula for permutations is NPR, where N is the total amount of objects and R is how many you're taking at a time. So let's say I had 5P3. It means out of 5 objects, I'm focusing on 3 of them. So if I had 5 balls and I had to pick 3, that would be 5P3. So hopefully this made a little bit more sense. There's also the possibility of cases. That means that there's more than one way to solve a question. Something like this that can be considered is if you're being told to find a certain amount of digits, a certain permutation between 1 and 100. You would have to account for the permutations of having 1 digit, the permutations of having 2 digits, and the permutations, let's just make this 1,000 to make this a little bit more fluid. You would have to find the permutations of having 3 digits as well, based on the specific scenario. And then, once you get all of the cases, so let's just say you got all the numbers for these, you would add them together to get your total amount of permutations. Let's go over some examples and hopefully this will make more sense. Alright, this is the first example that we're going to deal with. Question 19 asks, how many integers from 3,000 to 8,999 contain no 7s? We're going to start this question off doing the method I showed you earlier, which was to create a spot and find out how many objects are possible in each spot. For our spot right here, we know that in none of these spots can the number include 7. So let's start with this first spot right here. We've got 3,000 to 8,999. The difference between 3 and 8 is 5. But because we can't include the 7,000 area, that possible amount of numbers becomes 4. So for the first spot, we would have 4. Alright, so let's start with this first example. The question asks, how many integers from 3,000 to 8,999 inclusive contain no 7s? So let's start with the method I showed you earlier, where we start with 4 spots. We know that in this question, there are 4 spots because both of the numbers are in between the thousands. So it can't become like 100 or 10,000 because it's asking you to look in this area specifically. Let's start with the first spot. So between 3 and 8, let's write this down. 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4, 5, 6 digits. However, it can't contain any 7s. So we'd have to automatically eliminate this. That means that there are 5 possible digits for the first number. Now, we can follow a similar process with these ones, except these ones are less restricted than if we were to do the first digit. So we can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 digits total. But again, we can't include the 7, so we automatically eliminate that. Now we've got 9 digits left. This question does not specify that you can't repeat any digits. So you would do a similar process in your, hopefully mentally, like this. And you realize that only 9 digits can fall in these spots. You multiply these together to get the amount of possibilities, and you get 3,645. This question is asking you to show that these two things are not equal. So, we've got 4 factorial plus 3 factorial is not equal to 4 plus 3 factorial. The whole thing is factorial. Let's do what's in the brackets first. So we've got 7. And now we know that we're going to raise that to a factorial symbol. Let's just leave that side for now. 4 factorial is equal to 24. So let's just fully do the math on this side. And 3 factorial is equal to 6. This side equals to 30. 7 factorial is equal to 720. The trick that it's trying to show you with this question is that you're assuming that 4 factorial plus 3 factorial is equal to 7 factorial. However, that is not the case, because if you were to fully factor each one of these, fully simplify them, then you would not get 720. So when it's not bracketed, you assume that you were to do the process first and then add them together. Whereas to this one, you add together and then raise it to the factorial because of the brackets. All right, 7a and c are asking for 2 different processes. If you remember from earlier, I have this formula, and we know what each number means. So if we go back down, we've got an equation where we have to solve for n, and an equation where we have to solve for r. Let's start with solving for r. So we'll start with c. And let's fill in all that we know so far. So 6 factorial is equal to 6 minus r factorial, which is equal to 30. We can simplify this 6 to 720. Now we have to get this out of the bottom. So we would multiply it out, and by that we have to multiply it to the other side as well. Now here is where it gets a bit tricky. You still have that factorial symbol that you want to deal with. So let's get rid of the 30 here. Move it to the other side. 720 divided by 30 is equal to 24. 24 equals 6 minus r factorial. Now, the way that I would solve this is just elimination. We already know that 24 is equal to 4 factorial. To understand this, I would just figure out what r value can make the brackets equal 4. So r has to equal 2 in order for the brackets to equal 4. So 6 minus 2 factorial, 4 factorial is equal to 24. Okay, 7a, where we're solving for n. So we've got n factorial over n minus 2 factorial, which is equal to 30. There is a small hint that comes with being given the factorial symbol. We know that n has numbers below it, but we don't know what n is yet. So n saying, let's make up a number, 4 factorial can be simplified to 4 times 3 factorial. Or it can be simplified to 4 times 3 times 2 factorial. That's what we're doing here. Every digit after n will be 1 less because that is how the factorial symbol works. You're going to want to cancel out the n minus 2 on the bottom so you don't have to deal with it later. So just expand until you reach n minus 2 factorial, and then cancel those out. Now you've got n minus 1 equals 30. You can solve this with simple algebra. So we've got n squared minus n minus 30 is equal to 0, which is also further factored is n minus 6, n plus 5 equals 0. Your permutation values can never be negative. So you know that because this has a plus 5, this cancels out immediately. N equals 6. This is the last example I'll be explaining for 11.1. So, we know that this code has to be 4 digits. The first digit will be an alphabetical, and these 3 will be a number. We know that the first character can be any letter other than 0. There's 26 letters in the alphabet, and by removing 0, we have 25 options left. And then it says the last 3 characters are to be 3 different digits. That means we can't have any repeats in the last 3 digits. From 0 to 9, that's 10 possible digits. So we start off with 10, and then after you use a number here, it can't be repeated in the third spot. So we have 9 left, and then you've used 2, so you only have 8 left. Once you multiply this, you will get 18,000. However, that's not the number that the question is asking for. It's asking if they'll be able to assign each member a different ID code. But it has 25,000 members. And with only 18,000 codes possible, there will not be enough codes to give everyone a unique number.